This is example 9.5 from Discovering Design with Chemistry. A chemist wants to make 300 grams of calcium hydroxide via the following reaction. And then there's the chemical equation for us. If the chemist has 3 molarity solution of sodium hydroxide, what volume of that solution will he need to use? So let's just begin by labeling what we know and figuring out what we need. So here's what we want to make. So that means it's a product. So even if you don't recognize this is your calcium hydroxide, which I hope you do, but if you didn't, the first sentence helps us know this is a product. So we want 300 grams of this. And then we have a solution of this one, and that solution is 3 molarity, and that just means moles per liter. And they want to know what volume of that solution will he need to use. So we have a few different things we can work with. First of all, we know that when we have grams of something, in this case it's a product, we can convert it to moles, and then we can work in moles to get the moles of the sodium hydroxide, and then we could convert that one, if needed, back to grams. In this case, what we actually want to know is not grams, but volume. So we're probably going to have to use our new equation that helps us know what to do with moles, liters, and molarity. So let's start by converting our grams to moles, and we're going to work backwards through this. So we have 300 grams, and for every 1 mole, how many grams do we have? So let's find all of our things on our periodic table. All right, so we have calciums right here, and oxygens right here, and hydrogens right here. So we're going to add up those numbers. So we have 40.08 for the calcium, 16 for the oxygen, and then 1.01 for the hydrogen. And if we add all this up, we can figure out exactly what the atomic mass is for that and how many grams it takes to make a mole. All right, so 74.10, because everything has 2 decimal places, so we're going to keep that. So 74.10. So if we use this conversion, which we've been doing for at least a chapter or so, we can figure out how many moles of calcium hydroxide that we want to make. We know what it is in grams. What we need to figure out is what it is in moles. So we're going to take our 300 grams and we're going to divide that by that 74.10 that we just got. And we're going to want to keep 4 significant figures. So that's going to be 4.049. So 4.049 moles of our calcium hydroxide. All right. So we can use that to figure out how many moles of the sodium hydroxide that we need to use. So let's start with working our way backwards from 1 mole to another. So for every 1 mole that we have of calcium hydroxide, we must have started with 2 moles of sodium hydroxide. And I just got that from the one that's not there, but the one that we know is there, like the assumed one, or the, I can't think of the right word, the invisible one, and the 2 that's right here. And I'm going to convert the moles of calcium hydroxide to moles of sodium hydroxide using that. So I have 4.049 moles of calcium hydroxide So I put my 1 here and my 2 here, and these are both moles. All right, so this cancels out the moles of calcium hydroxide, leaving me with moles of sodium hydroxide. and then I just multiply that by 2, and then I keep, again, 4 significant digits. So 4.049 times 2 gives me 8.098. All right, so now I know how many moles of the thing that I'm trying to find the volume of. I have the moles. So let's go back and look at what we have. We have moles. If we want to use this, because this is the only thing we know of that includes volume, this little path that we have been taking that could have led us back to grams, we know how to convert between grams and moles because we use the periodic table to help us find that molar mass to convert back and forth. But now we have something new that can help us convert things into a volume of a solution that contains that thing. And so we have moles. The initial information gave us that it was 3.00 molarity, so we have molarity. What we don't have is liters. So let's take this and let's rearrange it. So if we swap these two, we're going to multiply both sides by L and divide both sides by the big M. We can rearrange it. If you didn't follow what I just did, pause and work it by hand, where you multiply both sides by the L and then divide both sides by the big M, and you'll see that you get this. So now we can take what we have and we can find the liters of the volume that we need. So, in fact, I probably should change the L to V. Let's do that. Well, let's leave it L over there and we're going to make it be V over here. So we're going to call it volume, which is going to be in liters. The volume of moles over this. So our moles is 8.098 moles. And then our molarity is 3.00. And I'm going to write moles per liter. And this moles cancels out. And I have a liter on the bottom of a fraction on the bottom of a fraction, which means my end result will have the liter as the only unit left, not under a fraction. All right, so we get to keep 3 significant figures, so 2.70, and that's in liters. 2.70, and that's what we were looking for, is what volume we would need. We would need 2.7 liters, and because the concentration is 3.00 moles per liter, and we want 8.09 moles, this is the amount of liters that we need to get that. And you can kind of see how that is. If there are 3 moles per liter and we want just under 9 moles, that would be just under 3 liters, which is what we got. So sometimes when you get the answer, pause and think, does that make sense? And if it makes sense, then it's probably a correct answer. All right, so again, with this problem, all we're doing is combining what we did in the last chapter with converting between grams and moles, and working across the chemical equation with our new molarity formula where we use moles per liters mixed into this.